Welcome to qnawire.
All right. So for this problem, we have an LRC series circuit, and so we know the voltage amplitude is V, and also we know the frequency. So for part A, we want to show that the current amplitude is given by this formula. So we know the current in the series circuit is just I equal to V over impedance. So for the LRC series circuit, the impedance formula is just square root R squared plus omega L minus 1 over omega C squared. So this is the formula for the current in the LRC series circuit. So this is very straightforward. And for part B, we want to show that the average power dissipated in the resistor is given by this formula. To do this, so if we look back on the current, we see that this is actually the current amplitude. To figure out the power, we need to transfer the amplitude into the RMS value, and the relation is I RMS equal to the amplitude over square root 2. Okay. Then the power dissipated on the resistor is P average equal to I RMS squared times R. So this is the average power dissipated on the resistor. And if you plug in this formula into here, you will get the exact formula shown here. And for part C, so it asks us to show that I and P are both maximum when omega is 1 over square root LC. So this is actually very easy. If we look at these two formulas, we see that the only part depends on omega is in the denominator. So this is omega L minus 1 over omega C, and we also have this formula here, omega L minus 1 over omega C. So to maximize the both formula, we simply need to set omega L equal to 1 over omega C. So this is the resonant condition. By setting this condition, we can minimize the denominator for both formulas, and so that we can maximize both formulas, the I and P. And this will give us solution omega equal to 1 over square root LC. And for part D, so we want to graph P as a function of omega. So by using these parameters. So I've already shown the drawing here. So this is the drawing. And the x coordinates is the omega, and y is simply the value for P. So we also need to compare to the light purple curve in this figure. So the figure is shown here. As we can see in the light purple one, which is this one, we see that we have a very sharp peak over here. So this is almost the same behavior as this diagram. We see that they also reach the peak value when omega equal to 1000, right? So they have the same behavior. And discuss the behavior. Yeah, we already discuss the behavior I and P in the limit omega equal to 0 and omega to infinity. So for both figures, when omega is 0, omega to infinity, they are both equal to 0, 0 and 0. So 0 and 0. Okay. So these two figures, they have the same behavior. Okay.